Inside the human brain, roughly 86 billion biological neurons continuously fire electrical impulses across synapses to process information. To replicate that organic process in code, we move from the optimization mechanics of gradient descent to algorithm number 35, the perceptron. In 1957, psychologist Frank Rosenblatt moved this biological concept out of software simulation and into reality. He built the Mark I Perceptron, a massive room-sized machine utilizing 400 photocells wired to association units, whose weights were set by physical, motor-driven potentiometers. The media reaction was deafening. In 1958, the New York Times declared that this machine was the embryo of an electronic computer that would soon walk, talk, and be conscious of its own existence. We have to separate the mid-century science fiction from the actual mathematics. If we strip away the room-sized hardware and the newspaper headlines, we find a tiny, elegant rule hiding underneath. Strictly speaking, the algorithm solves a very specific spatial problem. It is a linear binary classifier. It takes labeled examples of two distinct classes and calculates how to draw a single straight line right down the middle to separate them. This chart shows how this plays out. Plotting animals by their size and domestication, the dogs and cats cluster into distinct areas. The algorithm evaluates these coordinates, mathematically tilting and shifting a boundary line until the two groups are perfectly isolated. It is not performing original thought. It is simply solving a spatial puzzle designed to physically slice a coordinate plane in half. This diagram shows the specific anatomy of that artificial decision. The algorithm ingests a vector of input data. It multiplies each input by a specific learned weight, adds a constant bias, and compresses them all into a single number called the weighted sum. Geometrically, those components control everything. The weights dictate the exact tilt of the boundary line, while the bias shifts that entire line left or right across the space. That weighted sum then hits the final phase, the step activation function. Also known as a Heaviside function, this acts as a hard threshold. If the total clears 0, the neuron fires a 1. If it falls short, it outputs a 0. Despite the biological metaphors, this artificial intelligence relies on a rigid mathematical voting system governed by a fixed threshold. To draw its boundary line accurately, the algorithm learns from its mistakes. It uses an error correction mechanic that calculates the exact difference between the true, expected label and its own prediction. The behavioral logic here is highly efficient. If the neuron guesses correctly, that difference is 0, and the formula ignores the data entirely. It only nudges its weights when it gets the answer wrong. This truth table shows a classic AND gate, where the output is only a 1 if both inputs are a 1. As the algorithm evaluates these coordinates, it makes errors, adjusts its weights, and tries again. After a few cycles, the neuron converges. The weights lock into place, snapping the decision boundary perfectly across the graph to isolate the single positive coordinate from the 3 negatives. This yields a famous mathematical guarantee. If a dataset is linearly separable, the perceptron learning rule will always converge. The machine successfully classifies the world purely by reacting to its own failures. The single artificial neuron we've just mapped out is the exact arithmetic hiding inside modern artificial intelligence. When you take this simple rule, a weighted sum passed through an activation function, and duplicate it by the millions, you form the dense, interconnected layers driving today's deep learning models. We have the historical context, and we understand how the math physically separates data in space. Now we are ready to open the neuron itself and translate that logic into code, line by line. It takes the total weighted sum and decides, does this neuron fire or stay quiet? When we translate this into Python, we often use a smooth curve called a sigmoid function. Frank Rosenblatt's original 1958 perceptron used a hard binary step. It either fired a 1 or a 0. The sigmoid function takes that same input, z, and mathematically squashes it down into a softer decimal value, somewhere perfectly between 0 and 1. Or we can swap that out for a modern standard like ReLU. The math changes. Here, any negative input simply returns 0, while positive inputs pass right through, but the core purpose is completely identical. This software decision point dictates the final output of the artificial cell, filtering the signal before it reaches the rest of the network. That explains how a neuron fires, but how does it actually adapt and learn over time? Look back at our diagram, specifically the orange summation node and the learning rule at the bottom. This is where the actual learning takes place. In code, the perceptron learning loop hinges on this exact comparison and tweaks the weights if it got it wrong. At this level, a machine learning from experience is quite literally a line of subtraction deciding whether to adjust a number. This isolated math scales up directly into the deep learning architectures used in modern software engineering. To build massive neural networks quickly, developers use high-level frameworks like TensorFlow's Keras. This is a real-world block of Keras sequential architecture, the kind of code you would write to classify complex data like handwritten digits. Notice this single line defining a dense layer. That layer is exactly 128 of the individual perceptrons we just analyzed, stacked side by side, processing the data together. The parameters typed into this Keras function map directly back to the conceptual nodes of our single neuron. The dense layer handles the orange-weighted sums, and the ReLU parameter plugs in our violet activation gate. Deep neural networks, regardless of how complex their final outputs seem, are ultimately built on massive, stacked repetitions of these simple weighted sums and error nudges. Modern AI architectures are built on this basic arithmetic repeating at a massive scale. But an individual artificial neuron is computationally fast and beautifully simple, which means a single straight line can only solve so many problems. So where does this algorithm shine in practice? And what happens to a single perceptron when it encounters real-world data it simply cannot split?
In an era of massive language models, where does a single artificial neuron actually earn its keep? And when does it hit a wall it simply cannot climb? The perceptron finds its utility in modern production as a specialized tool for blazing fast, incredibly lightweight binary classification. Engineers deploy this logic when they need a rapid yes or no decision on a high-velocity stream of data, separating a legitimate email from a wave of spam, or flagging a single fraudulent transaction in a torrent of clear ones. Its primary advantage is online learning. Instead of storing a massive historical dataset in memory and analyzing it all at once, the perceptron processes a live data stream, one single example at a time. While it is the hardware ancestor of all modern AI, its exact geometric logic remains the active foundation inside today's massive-scale linear models. An engineer reaches for this specific algorithm over a heavier deep neural network when they need predictability and extreme efficiency, and a zero if it isn't. Because of this structure, the space complexity is O of D. To deploy this, a system only needs enough memory to hold that tiny vector of weights and one bias number. The prediction time complexity is also O of D. When a new piece of data arrives, classifying it requires only a single, fast mathematical operation known as a dot product. Training cycles are equally efficient, sitting at O of E times N times D. The training time scales strictly linearly across the number of passes, the number of examples, and the number of features. But to use this algorithm, you must meet one absolute non-negotiable prerequisite. Your data must be perfectly linearly separable. If a straight line can theoretically separate your two categories, the perceptron comes with a guarantee. It will find that line. We can calculate the exact upper limit of its learning process. The mistake-bound guarantee proves that the perceptron will only make a finite, predictable number of errors before converging on a perfect split. On linearly separable data, the perceptron behaves as a mathematically provable, finished tool. The limitation is right there in the requirement. Real-world data often refuses to be neatly split by a single straight line. Look at the left of this graph illustrating the XOR problem. The output is true only when inputs differ. Mapped on a 2D plane, they sit in a checkerboard pattern. This layout creates a geometric impossibility. No single straight line can cleanly separate them. In 1969, Marvin Minsky and Seymour Papert published a book called Perceptrons, which rigorously proved this limitation. They showed a single-layer perceptron was mathematically incapable of learning XOR. That proof collapsed confidence in the field. Funding dried up, research stalled, and the industry entered a decade-long freeze known as the first AI winter.
An algorithm's mathematical purity becomes its greatest liability the moment the environment it operates in becomes inherently nonlinear. Modern engineers follow strict deployment rules based on these limits, but the way to loan Perceptron if your system needs calibrated probability scores. It cannot provide a confidence percentage, only a hard 0 or a hard 1. Furthermore, if you feed it non-separable data, the algorithm loses its mathematical guarantee. It will cycle infinitely, endlessly adjusting its line without ever reaching convergence. Look at the right side of this diagram. This is the architectural mutation required to survive the XOR problem. By stacking multiple perceptrons into hidden layers, the network can mathematically bend the decision boundary. Complex problems are suddenly solvable. You can find the exact specifications and code implementations for this algorithm in Chapter 8 of 50 Algorithms Every Programmer Should Know by Emran Ahmad, available on Amazon and Pact, with more resources at neuralsca. From a room-sized machine of dials and photocells to the single line of code inside every dense layer, the perceptron is where deep learning begins, and the trick that finally let those stacked layers learn is its own story.